Alright, so welcome calculus students. This is our final example for section 2.5, related rates. And this is a circular motion problem. Some of you may remember that from physics, you took it last year. So a circular wheel with a radius of 2 feet rotates at a constant rate of 720 RPM. So I want to find dx dt in feet per second when theta is equal to 60 degrees. So what this is asking, so if I've got a circular wheel, this wheel is rotating around, and I'm going to make it rotate counterclockwise so that the angles correspond to the unit circle. So it rotates at a rate d theta dt of 720 RPM, which is revolutions per minute. We'll get back to that in a moment. And the circle, or the wheel, has a radius of 2 feet. Instead of writing r, the radius of the circle is constant throughout, and so it's a constant, not a variable, so I'm just going to write it as 2 feet. Alright, and so what this problem is asking me to do is to find dx dt when theta is 60 degrees. Okay, so if I look at a point on this particular on this circle, then this point is moving in a dy dt direction, but it's also moving in a dx dt rate as well. Excuse me. And so as you go around the circle, like for example at 0 degrees over here, then there would be no dx dt. There'd be only a dy dt. And at 90 degrees, there'd be no dy dt. There'd only be a dx dt. But at around 60 degrees, we have both. But we're only looking for dx dt in this particular case. Okay, so we got to put in our variables. So here, this angle here, I'm going to call theta. And this angle is changing at a rate of 720 RPM. And then at the center of my circle, if I put my traditional xy axis, then this length right here is going to be x, which is also a variable. And so if I have draw my geometry, I actually have a triangle here. And this side is x, and this is theta. And the hypotenuse is the radius, which is a constant 2 feet. So it's just actually a right triangle problem. And x is varying and theta is varying. Now, the one thing we need to do before we begin is, you see how this up here, our d theta dt, is in RPM. And you may remember this from physics. If you're given it in RPM, we've got to change this into radians per second. So I'm going to go ahead and do that conversion right now. So let me rewrite this. So this is d theta dt is equal to 720 revolutions per minute. And you always want to get that into radians per second, especially because we're asked for our dx dt in time is in seconds. Okay, so I'm going to have to do some unit conversions here. So the first unit conversion is, I know that 1 revolution of a circle is 2 pi radians. And the second conversion is I need to convert my time. So if we're asked to find dx dt in feet per minute, I wouldn't have to change the time. But in this case, I have to change it to seconds. So I know that 1 minute is equal to 60 seconds. And so when I multiply all this out, I get d theta dt, which is the constant rate that the circle's moving around. And just from physics, if you remember, this is called omega, which is the angular speed. And so d theta dt is going to be plus 24 pi radians per second. And so in this particular problem, what we want to do is we want to find dx dt when theta is equal to 60 degrees. Okay, now stop and check this. Whenever we're dealing with calculus, remember, you want everything to be in radians. So we need to convert this to radians. So our theta is actually equal to pi over 3 radians. So make sure you get it into radians before you start. And remember, we're not going to plug, because theta is a variable, it's changing in this problem, we're not going to plug this number in until the very end. Okay, so if we go back over to our triangle over here, x is changing and theta is changing, but the radius of the wheel remains constant. And so we have this really a right triangle relationship. So x is the adjacent side, and so my relationship that I'm going to differentiate is going to be cosine of theta is equal to adjacent over the hypotenuse. And I'm actually write this as cosine of theta is equal to 1/2 x. Okay, so what I'm going to do now is I'm going to differentiate this. I'm going to add a page. Okay, so I'm going to rewrite what I have. So I have cosine of theta is equal to 1/2 x. So now I'm going to differentiate both sides with respect to time. And if I do that, I get minus sine of theta, d theta dt, is equal to 1/2 dx dt. And here I'm trying to solve for dx dt. So dx dt, if I multiply both sides by 2, is equal to minus 2 sine of theta times d theta dt. And this problem is actually relatively simple because I don't have to go back to an earlier step to find anything. So I've got minus 2, and then my theta value that I'm being asked to find, this et, is pi over 3, which is 60 degrees. But remember, you have to put the radians in. And then d theta dt was plus 24 pi radians per second. And so if I multiply that all out, then dx dt at this particular location is going to be minus 24 times the square root of 3 times pi. And then in order to get the units, remember, you're looking at what the units of dx dt would be. And so our units are in feet in this problem, so dx is in feet, and it asks for time in seconds, which we have over here. So my units are just feet per second. And that is it. Now, why is this minus, and should it be minus? Let's just double check. So let's go back to our drawing. And at 60 degrees, if I call my wheel counterclockwise, then dx dt would be negative because it's moving to the left. So that answer is correct. So that's how you do the rotational motion problems, relatively easy. All right, and that's the 2 examples, and I will answer questions tomorrow in class. All right, have a good rest of the weekend.